And hello, 8-Bit Physics students. We're going to do another example problem for you tonight. We are going to do problem number 41 from chapter number 7. And this problem is going to involve conservation of momentum in dun 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 2 dimensions. 2D. So, let's get started. The problem says here that an eagle of mass 4.3 kilograms is moving with a speed of 7.8 meters per second and is on a collision course with a second eagle, 5.6 kilograms, moving in a direction perpendicular to the first. After they collide, they stick together. What will be the direction and speed of the two eagles after the collision? So let's do a little drawing here, and I am just going to apologize from the beginning. I tried to practice drawing eagles before this video, and that's about the best I came up with. So that is artistic is not one of Mr. Kirsten's strong points, you might say. Anyway, we're told that Eagle A has a mass of 4.3 kilograms, and the velocity or speed of Eagle A is 7.8 meters per second. And we'll say that this is in the plus x direction. All right, so we got to define some type of coordinate system here. Now, the only way I could think to draw another eagle was from above. Oh gosh, look at that. That's an eagle from above. Oh man, I am not an artist. Whew. Okay, so that eagle's going to be flying like that, and then they're going to collide. All right, and we're told that Eagle B has a mass of 5.6 kilograms and has a speed of 10.2 meters per second. And the question is, after they stick together, how fast are they going and in what direction are they going? Okay, so this problem really does break down to be conservation of momentum in two directions. So the momentum in the x direction of the system will be conserved and the momentum in the y direction will be conserved. Why are they conserved? Well, we're going to assume here there's no external forces acting on the system. So if that's the case, we can assume that the initial momentum of the system will equal the final momentum of the system. Pi equals Pf. Well, what is the initial momentum of the system here? Well, let's calculate Pia, right? The initial momentum of Eagle A. What a gracefully drawn eagle there. So that would just be the mass of A times the speed of A. Right? So if we plug in those two numbers, multiply them together, we will get 33.5 kilogram meters per second in the plus x direction. Okay, so this would be the momentum of Eagle A to the right. Now the initial momentum of Eagle B would be the mass of Eagle B times the speed or velocity of Eagle B, right? So if we plug in the mass and speed of Eagle B, we would get 57.1 kilograms times meters per second, and this would be in the plus y direction, okay? All right, so if I add these two guys together, I should get the initial momentum of the system. So Pia plus Pib would be the initial momentum of the system, and that should equal the final momentum of the system. Okay, so let's go off to the side here and just do a little drawing here, right? How do I add together vectors? Well, you can put them head to tail. Right? Here is head to tail, just like the eagles. This is the initial momentum of Eagle A, right? So this would be the total initial momentum of the two eagles together, which would also be equal to the final momentum. Now, if you look at this vector diagram, it kind of makes sense. After the eagles crash together, what direction would they go? Well, they would go that direction, right? So the momentum of the system beforehand is the momentum afterwards. Okay, well, let's do a little bit of math here. Let's see here. So what would the final momentum of the system be here? So the final momentum, right, the PF, right, I would have to do the Pythagorean theorem if I wanted to know the magnitude of PF, right? So this would be equal to the square root of the magnitude of PIA squared plus the magnitude of PIB squared, right? So to find the length of this triangle, the magnitude of this vector, I'd take the magnitude of this square plus the magnitude of that square, take the square root, and I would get square root of 33.5 squared plus 57.1 squared, and I type that into my trusty calculator, and then I get that PF, the magnitude of PF, is 66.2 kilogram meters per second. So the total momentum of the system, both before and after the collision, is 66.2 meters per second. So if I wanted to calculate, and that's also equal to the mass of the two eagles times the final velocity of the two eagles, right? Since the final momentum has to be the mass of the two eagles stuck together, right, times their final speed. So if I do a little math here, I could get that VF is equal to PF divided by MAB, okay, which is 66.2 divided by 4.3 plus 5.6, and so that gives us a VF of 6.7 meters per second, right? So when the two eagles stick together here, right, they will be moving in this direction at a speed of 6.7 meters per second. So that's just conservation of momentum. All right, Mr. Kirsten, but the problem asks for both both a speed and a direction. So how about we solve for this angle theta in here? Well, we could just use a little trig here. We could say that the tangent of theta, right, if that theta is right there, would be equal to the magnitude of PIB divided by the magnitude of PIA, right? So TOA, right, tangent is opposite over adjacent. So we could say that theta is the inverse tangent of, what do we say, PB is 50. Ooh, PB, peanut butter. That sounds good. Ooh, Mr. Kirsten's hungry. Okay. All right. Right. So plugging in my numbers here for the magnitudes of PIA and PIB, right? We would get that theta is equal to, comes out to be like 59.8 degrees or something like that. So to significant figures, theta would be 60 degrees. And we should label this angle somehow. So why don't we say counterclockwise from plus x axis. Okay, so that would be the direction that the two eagles would go after the crash, right? So they crash together, right? And then this angle would be 60 degrees in here, which kind of makes sense, right? Because you would be heading more north there, right? More in the positive y direction, right? Because this guy's a bigger momentum, right? This guy's, I probably didn't draw this to scale, right? This side should be almost twice as long, twice as much momentum as this side. All right, well, nice job, physics students. We got a little cartoon here to make you laugh for hanging in there with us, so stay tuned for that. All right, here we go. Your joke, a little xkcd.com, cartoon number 953, a funny website you should check out. On a scale of 1 to 10, how likely is it that this question is using binary? 4. What's a 4? Get it? Because it is using binary. So a scale of 1 to 10 on binary is really kind of like 1 to 2, right? Because a 10 in binary really means 2 to the 0 power plus 2 to the first power, which would just be 2. So it's a scale of 1 to 2, but 1 to 10 is binary. So 4 would be 100 in binary, right? That would be, oh my gosh. Oh, well, that's a funny little bit for you. A bit, because that's binary for a 1 or a 0. So, computer programmers would think this was hilarious. All right, nice job, physics students.